Hey guys, BuildZoid here, and today I want to complain about something that just annoys me. And technically I've already made a video about this topic before, but I'll try make this one shorter. So basically, I'm working on the PCB breakdown for the Asus Strix X870i gaming Wi-Fi motherboard, you know, the ITX Strix board. And it's a high-end Asus motherboard, so of course it uses SiC850A smart power stages from Vishay. And these are nominally 110 amp power stages. Now, for my PCB breakdowns, I always sort of have the like expected efficiency numbers for the power stages, and I get those numbers from the documentation from the manufacturers. Now, the first problem with these SiC850s is that they do not have public documentation because they're probably because they're exclusive to Asus. Like, yeah, nothing comes up on the Vishay website. I've tried like searching them before, and it's just they don't show up anywhere. Which again, I think it's probably because they're exclusive to Asus. Now, we can get 840s, we can get 820s, but yeah, no 850s. So that's annoying. So the next best thing I can do to like try get some idea of how efficient a SiC 850 might be is to look at the documentation of the 840s, because the 840s are 100 amps, so they shouldn't be that different from the 110 amp parts. And actually, I guess to prove the point, like let's pull up also the documentation for the, I mean, it's not documentation, it's like a product brief for the 80 amp parts. So anyway, here's the SiC 820s, 80 amp VR power smart power stages. Yeah, so these have a peak efficiency of like 93% at 1.8 volts output voltage, 600 kilohertz switching frequency. Um, that's honestly kind of terrible for something that's advertised as an 80 amp power stage, but I don't know the measurement methodology here. As in, like, I don't know if this includes the inductor losses. Does it include VRM controller losses? Does it include PC, like, power plane losses, right? Like, I don't know. It doesn't say. So that's annoying. But either way, this efficiency, kind of terrible. But so this is an 80 amp part, right? And you go from the 80 amp part to the 84 amp part, and you'll notice that like the curve is a bit like, you know, it falls off less, but the peak is still basically 93%. It's also a bit later, right? Like previously, yeah, like you can see how like basically the drop towards that 40 amp output is faster. Like the drop in efficiency on the 80 amp parts is steeper than on the 100 amp parts. But it's not that big a difference, right? Like it just isn't. It's really not that big a difference. And both of them have a peak efficiency of like 93%, which is kind of terrible. And I like hopefully it's just due to the measurement methodology being used and not because these are actually incapable of going above 93%, because now we're going to take a look at some power stages that are nominally similar output current ratings or lower output current ratings, but with expected efficiency graphs that are way better. And the first one we're going to look at is the SiC 620. The 620 is advertised as a 60 amp power stage, also made by Vishay, and really old. This was like popular for like RX 580s. Like you can find RX 580s that use this power stage, and also like Z390 motherboards, I think. So yeah, pretty old power stage, 60 amps. You'd imagine that it's probably less efficient than a 100 amp part that came out. I think sometime in like 2021, whereas this is 2020. Well, this one had a few revisions. Well, this did too, I guess. So that's not helpful. But anyway, yeah, so this 60 amp part has a peak efficiency for an output voltage of 1.8 volts um, of like over 94% at 15 amps output. Like its efficiency at 20 amps output is still higher than the 820. Like, you know, at this point it's already falling off. Like we're past the peak efficiency, right? That's at 15. So at 20 amps it's already like we're already past the peak efficiency. Still apparently better than the peak efficiency of a 90 amp or even a 100 amp smart power stage from Vishay, which is pretty weird. So I would assume this is probably down to some massive difference in measurement methodology. But that's still infuriating for me when making PCB breakdowns because most power stage manufacturers have graphs that look a lot more like this than this. And so it basically makes the Vishay parts either look like if I just take these efficiency numbers and I like do the calculations for the expected efficiency of the VRM on the Strix, it looks terrible. It might actually be terrible. It's really hard to test that in isolation because like short of like building test boards with like one power stage, you have a PCB one power stage and like a standardized inductor, and then you just like run different power stages on the same test board to see how their efficiency behaves. Yeah, short of doing that, isolating the efficiency of the power stage as the like driver of the VRM thermal behavior is kind of difficult because if your VRM is slightly less efficient than your competition, or even a lot less efficient than your competition, you could just throw a bigger heatsink on it, right? Like if you just throw a big enough heatsink on the VRM, you can very quickly solve any like a couple watts more heat dissipation, which is from an efficiency perspective actually a big deal, right? Like if your VRM, like let's say you're outputting, like let's say for, like I'll just pull up the calculator for this. That's going to make this easier. Oh, of course, I have a random calculator instance already hanging around. So let's say, you're outputting 200 watts and that's with, say, 90% efficiency. So you have a heat loss of like 22 watts, right? So you're producing 22 watts of heat. Well, 22.222, you get the idea. And then let's say we have an efficiency of 91%. Well, that produces about 20 watts of heat. So it's like 2 watts difference or 2.5 watts difference in this case. Not a lot of difference, right? Like that's not a lot of difference in total heat output. So like this is easily solvable with just a bigger heatsink or a differently laid out power plane or like, like you could just change the layout of the MOSFETs and it would probably get you that temperature difference. So that's, and then of course if you're at like 200 amps and let's say your VRM is like crazy efficient, 95% efficiency, that's still just 10 watts. A big heatsink can deal, like, you can cover, well, I mean, you're probably not going to get, like, you're not going to, like, I think even with the big heatsink, your VRM is going to end up noticeably warmer at that point when it's like a 10 watt difference in efficiency. But it's not going to be so big that it's concerning, even though that's like a pretty massive efficiency difference, right? So, yeah. And also like when doing the comparisons for the motherboards, right, in my PCB breakdowns, well, a motherboard that has like 90% efficiency in like expected efficiency for the VRM, because this is an annoying limitation of the PCB breakdowns. The real world efficiency of the motherboard is often going to be a lot worse than the theoretical best case, like the theoretical efficiency of the power stage itself, because you also have like power losses in the CPU socket, power losses in the power plane, power losses in the, like the inductors might be worse or better than what the, actually I'd say usually they're worse than what the power stage manufacturer is using, because the really high current inductors don't tend to be very conductive of not producing coil whine. Just like fun fact, the loudest inductors are generally the really high current ones. And I don't really know why that is. That's just like a thing that I've noticed, is that the most coil whine usually comes from the really, really high current inductors. But anyway, I guess because they're primarily meant for like server applications, and in server applications, just nobody cares if there's a bit of coil whine because you're not going to hear it over the fans anyway. Because you'll be actually you won't hear it because you'll be wearing earplugs if you're inside an actual data center, especially when it's running. But anyway, yeah, yeah, so you know that's just like and like a limitation of the PCB breakdowns. And it's annoying, and it annoys me a lot. But it annoys me even more when I end up with this situation where it's like, oh yeah, these parts that are supposedly like super high current rating, and then the peak efficiency according to the manufacturer is like kind of terrible, especially compared to other parts from other manufacturers. Um, right? So like Vishay had a 60 amp part that's like more peak efficiency. Actually, just more efficient. Like even at 30 amps output, this still looks more efficient, right? And this is the kind of scenario where I'm like looking at this efficiency graph, and it really makes me wonder, like, so would the VRM on the ITX Strix actually run cooler if you put a bunch of SIC 620As on it instead of the eight, like instead of these? Actually, it probably would. Like, we don't even need to worry about the 30 amp end of the graph because it's a motherboard for Ryzen CPUs. It's a 10 phase, right? Like, max output current is going to be somewhere between, depending on the CPU, you're going to be at like 100 to like 250 amps. So you're going to be in this range, right? And in that range, the 620 just looks way better. At least on paper, it looks way better. And so at that point, that really does make me wonder, like, would it actually run cooler? Because that would be stupid, wouldn't it? If a 60 amp power stage gave you a cooler running motherboard than a 110 amp part. But anyway, and then you look at some other manufacturer data sheets, like say Infineon. So this is a 90 amp part from Infineon. This thing apparently can achieve peak efficiencies for 1.8 volts output voltage up to 97%. Also, this is probably the best power stage that currently exists. I'd really like to have evidence of it actually being the best, but that would require making like a test board and testing it directly. But yeah, and Infineon does point out that like they're no PWM controller loss, no inductor loss, like this is just the power stage. No, that's still crazy. And actually the 620A says yeah, this says only the losses of the power stages again. Right? And here we don't get told if like does it include the inductors? Like honestly, with how low that efficiency is, I'm thinking like this has to include the power plane and maybe even a socket or something or like a BGA because 93% for something that's supposedly a 100 amp power stage is just like that's kind of terrible when you have like a 60 amp part that claims higher peak efficiency. And then there's like the TDA 21472 from Infineon, which is a 70 amp part, you know, just under 95%, well over 94% efficiency for 1.8 volts. And again, no PWM controller, no inductor loss, just the power stage. And we have monolithic power systems, MP87180. This isn't used on any motherboards I'm aware of. At least I've not seen it on any motherboards. Yeah, this claims a peak efficiency of, again, over 94% because that's just kind of the peak efficiency. Like, this is what I expect to see in a datasheet for a high current power stage, right? So you can imagine my frustration when then I get to the freaking Vishay parts that, like, Asus is using, and it says 93%, and it's like, they have to be like including the PCB power losses, right? Like they can't actually be this bad. Because if this is just the power stage, these are terrible. Um, um, yeah, so anyway, so like 80 amp part from monolithic power systems. Like again, also the efficiency curve here. Well, the issue with like, oh, the curve looks very similar to the Infineon one. Well, this one goes all the way out to 80 amps, right? That's another fun thing with a lot of these power stage data sheets. Like this ends at 60. This ends at 60. Because the thing is, once you go past 60 amps, honestly, not even 60, like once you go past like 40 amps output current per phase, the inductors, like everything starts becoming a problem. Like the heat density of the power stage, like even if it's very efficient, the heat density becomes a massive problem. Your inductor starts being like everything starts being a massive problem once you go past 40 amps output per phase. So it doesn't really make sense to have data sheets for these like really, because the nominal current rating is more like a performance class in a way than it is an actual like, hey, you're gonna want to put 90 amps through this, because no, you won't. Like it's just not gonna be practical. Um, but yeah, so the documentation will regularly end at like 60A, but then you look at these Vishay parts and they end at 40. Which, like, to be fair, I did just mention that past 40 amps things kind of stop being practical, but like, um, their old stuff went to 55 on a 60 amp power stage. Anyway, then there's the FDMF 3170. This is a 70 amp smart power stage from On Semiconductor. All right, where does it say? Oh yeah, rated output current, 70 amps. Now this thing runs into that same problem of like, oh, they don't actually spec it all the way out to 70 amps because, yeah, you wouldn't actually want to run that. It ends at 60. That's just kind of where they usually end. Honestly, I'm surprised that Monolithic Power Systems ends this datasheet at 80 amps. And you can, well, here you can really clearly see why 80 amps through an 80 amp part is a bad idea, because that is 18 watt, like that's like, yeah, well, it's like 19 watts of power loss at that point, right? So you have um, like your little power stage with its, I'm not sure what the package is made of, but it's not metal. It's not like it is. It's not like it's not a huge thermal insulator, but it's not like an IHS on a CPU. It's way worse than that. Um, so you have this like tiny little 18 like, so you have the little black chip, right? And then inside this chip there's like silicon. I'm pretty sure these are still silicon. They might, yeah, I'm pretty sure power stages still primarily use silicon. Um, at least the low voltage ones do, I think. Anyway, but so inside this, you basically have a like bit of silicon, and that gets really hot, right? And then you need to pull that heat out of it through this packaging, as well as through the board. In fact, the packaging material, as far as I know, is so bad as a thermal conductor that most of the cooling actually comes from pulling the heat out of the PCB. So you'll sometimes see, and now if you build a massive overkill VRM, this really isn't a concern. You can just cool through the packaging itself. It doesn't really matter. But like if you, like there are VRM designs where the designers are trying to cut down on, how many power stages they need, and you'll often see things like power planes that are just absolutely gigantic, so that the heat can sink into the copper of the power plane and then get pulled out of that through a thermal pad instead of trying to pull it through the freaking casing of the power stage. There are also thermally enhanced power stages where they'll just have like a metal heat sink embedded into the casing material. Those are really expensive because it just adds a bunch of it makes the manufacturing way more complex. Also, the metal part ends up being a short circuit hazard because it's connected directly to the switch node, so it has like 12 volts on it. Well, it doesn't have literal 12 volts on it, but it has the like switching waveform on it. So yeah, if your heatsink if your heatsink touches that, you've got a really bad day. Is what you've got. So normally that's not a concern because you have thermal pads, and heat sinks will normally have like standoffs to make sure that they don't sit too low. But yeah, like, so they're not super popular, but those are an option for really like squeezing all the thermal dissipation capacity out of a power stage as possible. But generally speaking, yeah, the 80 amps over here, this is like, you're not actually going to use that because you're just not going to be able to cool it. Like if you design your board and your cooling system to deal with this, then yeah, you can do 80 amps. But you probably don't want to do that because it's probably cheaper to just buy more power stages, and not end up in the, horrible efficiency end of the curve. Anyway, so the FDMF 3170. Now, unfortunately, this doesn't give us a nice clean efficiency curve for just a single power stage. But what it does give us is a efficiency curve for an entire voltage regulator, a 6-phase. I am not sure if this includes the controller losses, but I would imagine that it probably includes the inductor losses. Um, yeah, so this is a 6-phase, and probably the power plane losses. Now, the power plane losses are kind of a problem because, like, the power, like, at 200 amps, and, like, especially once you get to, say, like, 300 amps, the power plane starts being a major problem. Well, depending on the board, but it can be a massive problem. Whereas at low currents, yeah, the power plane doesn't really matter that much. But anyway, so 6-phase interleaved operation. This thing's running like 95%, right? And this is 6 power stages. So at like let's say like at 20 amps per power stage, that would be about 120 watts. So that would be somewhere in this area on the graph. You'd be at like way over 94%, right? So still like an entire percentage point. And the thing is, like, this is a 70 amp part. And it's an entire percentage point above what, like, Vishay is advertising for the SIC 840. Like, either Vishay has the most unforgiving test methodology ever, or these things suck. And yeah, and that is my problem with the SIC 850, is just like when I'm writing my notes for the PCB breakdown, they look really bad. And I did try to like isolate the SIC 850s in the past and do like a test where I tested a 16-phase Infineon VRM on a gigabyte board against the was that actually a 16-phase or was that 8? It might have been 8. It was 16 power stages, okay? We're not, like, it was 16 power stages. I think it was an actual 16-phase. The reason I bring that up is, like, you can have 16 power stages with 8 PWM signals, and then every 2 power stages are in the same phase with each other, because they're literally in phase with each other. You can't turn them on and off independently. They turn on and off at the same time. And then alternatively, you can have 16 independent phases. That's what the like interleaving thing is referring to over here. 6-phase interleaving is like you have 6 independent phases. But anyway, so I tested like 16 Infineon power stages on a gigabyte motherboard against 16 of the Vishay SIC 850s on an Asus motherboard. Both of them with no VRM heatsinks. The gigabyte board ran cooler by like several degrees. Even though, if I remember correctly, that gigabyte board was on TDA 21472s or 21470s, which are both 70 amp parts. So maybe this horrendous efficiency curve that Vishay has in their like data sheet and like, you know, product brief is real. And these things are actually really not very efficient at all. And they just have an insane nominal current rating, and I'm really annoyed about this. Because it's like, because basically what that means is that this nominal current rating is just utterly useless, right? Like, it doesn't mean anything if you can have a 110 amp part, which actually like has miserable efficiency, compared to like 60 amp parts and 70 amp parts and 80 amp parts and 90 amp parts and just like everything. Like, this is the kind of efficiency curve I'd expect from like a 40 amp. Well, okay, no, that's not true. If this was a 40 amp part, that 93% of efficiency peak would be at like 10 amps, not at 25. But still, that is really low efficiency. And so this is just like a frustration I have with working on the PCB breakdown for the Strix right now. And I'm going to have that same frustration when I'm writing the notes for the Hero, because the Hero also uses the SIC 850s, and Vishay's, like, the only public documentation for, you know, high current Vishay power stages is for the 100 amp parts, and those seem to suck. At least on paper, it looks like they suck. And I am very annoyed about that. Like, at the same time, I mean, on the Hero, it doesn't really matter because you have like 18 of them, I think. So the fact that the efficiency is low is not really going to affect the VRM thermals very much. I mean, the efficiency is still going to... The funny thing is when you get to the high-end boards, a lot of the time, most of them have so many power stages that you're like in this end of the efficiency curve. Yeah. Yeah, that's pretty typical because like 10 amps, like yeah, you're gonna be in like you're and that's gonna be for every part, right? Like you look at the TDA 21490, which I'm not 100% certain, but I do strongly suspect this might actually be the best power stage that's currently available. Um, unless there's some new, I mean, Renesas now has parts that they're advertising as 110 amps, so those might be on par or better than the TDA 21490s. But anyway, yeah, but even these, which are 90 amps, nominal output current, yeah, 10 amps output current, like they're not at the peak of their efficiency curve. I mean, they're still crazy efficient. 96% is wild, right? Because like a TDA 21472 doesn't reach 96% ever, right? Um, so whatever methodology Infineon is using, like the 21490s are like another 2% better than the 72s. So these are actually just insane because even at 10 amps output current, the efficiency is so freaking high. But you're still not at the peak of the efficiency curve, right? On the vast majority of high-end boards, you're not going to be on the peak of the efficiency curve. So it doesn't really matter, and the VRM thermals kind of like solve themselves because there's just so many power stages that the totals, like the combined surface area of those power stages is so high that you don't really need, like you don't need a VRM heatsink at that point. Um, right, and that's like once you have like 16 power stages, it just stops really being a concern how you cool it because there's just so damn many of them. At least for current like output currents of 200 amps or less. Once you go above 200 amps, you suddenly start needing a heatsink, and you also need to start worrying about whether or not the motherboard's power plane is properly designed. Because, yeah, there's boards out there where the VRM will actually run cooler than the PCB does, which is kind of, well, actually, I don't think that's not really a relevant concern for current gen boards, but for like in the past, that was like for Z590, there was a board that did that. And I think there's another Z490 board that does the same thing because I'm pretty sure that Z590 board uses the same power plane layout as a different Z490 board. Um, so, um, yeah, but that's not really a concern on Ryzen because getting Ryzen to pull more than 200 amps is really, really difficult. Um, and only relevant to the 16 core CPUs. But either way, this is just like a frustration I have. Is just like, why did Asus have to go and find some exotic Vishay power? Well, they're not really exotic, I guess. Like, I had the same issue when Gigabyte used the 820s. I think it was the 820s on the Tachyon, where it's like, but on paper, these suck. Yeah, I think that was the Z590 Tachyon that used the 820s. And I was like I was excited because it's like, oh, big smart power stages. Because up until that point, all the other like rectangular smart power stages I'd seen was like parts like the FDM F3170s, which are really good. And the set 21472s, and so it's like, oh, there's like an even higher current rating power stage, and then it's like, what? How is this higher current rating? This looks terrible. But anyway, yeah, so that's my rant about nominal current ratings and how they're like I wish they weren't a marketing thing. Because that's the whole, like, that's as far as I'm concerned, the main reason this whole thing has happened, that we have these like power stages with these insanely high nominal current ratings, is it's a marketing thing. Because like I mentioned earlier, you're never ever going to want to put the nominal current rating through a power stage, right? Like the efficiency is going to be horrendous, the heat density is going to be unmanageable. You're not going to do that, right? The reason you want a 90 amp smart power stage is not because you're going to run it at 90 amps output, because that's a terrible idea. It's not going to be coolable, right? The efficiency is going to be horrendous. The reason you want that 90 amp power stage is because at 20 amps output, which is a nice, reasonable amount of current to put through a phase, and very coolable, the efficiency is going to be sky high, right? So you're going to have even less heat to worry about. And then you're not going to put 20 of them on a board that only needs to output like 200 amps. Actually, you might, because again, like depending on what inductors you're using, like you might have like better thermals if you have more inductors at the same time. Though in that case, I would argue that you should probably just use better inductors instead of like throwing a bunch of power stages at the problem. Though, like, it depends. Right. But yeah. So yeah. So and the thing is, like, like all of the motherboard vendors are doing this, where it's just like there's just like an arms race to have the highest nominal current rating power stages, and it's just like it doesn't matter what the nominal current rating is past like 60 amps. And the reason it doesn't matter past like 60 amps is because the number doesn't tell you anything after that, right? Like 40 amp power stages are very consistently not great. 50 amp power stages are very consistently better than 40 amp power stages. So that's like a useful distinction, is like 40 amp parts are worse than 50 amp parts. And then you get to 60 amp parts, and 60 amp parts are generally consistently better than the 50 amp parts. So that's still a useful distinction. And then you get to the 70 amp parts, and the 80 amp parts, and the 90 amp parts, and the 100 amp parts, and the 110 amp parts. And this is where you get to the point where, like, wait a minute, some of these 70 amp parts run cooler than some of the 100 amp parts. The rate, like, the number doesn't mean anything anymore. And it frustrates me so much. Especially because it doesn't mean anything. It doesn't tell you if the board is good or not. It doesn't, like... And so I am very annoyed by that. Very, very annoyed by that. And now that I'm, writing PCB breakdown notes for Asus boards again, for AM5, I get to be frustrated by this. Again. I was really hoping that by X870, Asus would have used, like, a different power stage. But apparently, like, these Vishay parts, like, they like using these Vishay parts. And to be fair, like, it's not like the Asus motherboards have, like, VRM thermal issues or anything. But I am not convinced that these are actually the best power stages that Asus could have used. Because I haven't done a ton of testing on this, because also it doesn't matter that much. But, like, it just frustrates me when you have, because it's, like, my issue with it is that you have this marketing of, like, oh, these are 110 amp power stages. They're the most powerful, most bestest power stages. And then, like, I try to isolate the actual, like, thermal behavior of the power stages themselves, and they end up running hotter than 70 amp parts. And it's just like, and maybe I didn't, control for enough variables at the time. So maybe that's why they were running so hot. But, like, honestly, like, I don't think there's any scenario in which a 110 amp power stage should be running hotter than a 70 amp power stage, assuming that they're outputting the same amount of current, which they were. That was the one thing I went out of my way to make absolutely certain. Like, I couldn't control for the VRM switching frequency. I couldn't control for the inductors. But the output current was the same. And the 70 amp parts were running less hot. Now, maybe the PCB on the Gigabyte board was a better heatsink than the PCB on the Asus board, because again, I couldn't really control for that. But I would have honestly expected the reverse to be that like the Gigabyte board would have the less heatsinky PCB, but oh well. Um, yeah, and so that's like my whole frustration with this situation is just like the performance is fine. It's just that like you have advertising that is just not helpful, right? Like it does like it's actually just not helpful because it doesn't tell us anything at this point. It's just like it's just a meaningless number on the box. Another meaningless number on the motherboard box. Actually, it's not. I don't think they advertise it on the box, but on the website, right? Like you have the like, oh, we use 110 amp power stages. They could tell me they use fair like unicorn dust power stages. It would have the same amount of meaning at this point because the nominal current ratings for power stages past 70 amps just don't mean anything. At least not for the Vishay ones, as far as I can tell, because like I don't get it. Like, why did they change methodology? Um, I wonder if I pull up some other uh power stage from Vishay that's also like a high current rating. 840, 840. I don't want the 8 series. Oh, there's like an 830. It's gonna be the same curve, isn't it? Yeah, the same curve. Um, 60 amp. Does this have a performance curve? 645. Is this from current year at least? No, this is from 2020. Okay, so this is gonna be if there's performance curves. This is gonna be yeah. You know, these graphs look a lot like the ISL 99227B. Yeah, this looks like a grayscale version of the ISL 99227B power stages. Um, Also approaching 96% and doesn't include 5-volt losses. Um, oh, wait, no, they have includes 5-volt losses, and it's still way above 94%. And it's on higher inductance Wait, is it? Yeah, it's on higher inductance inductors. I mean, they could be lower DC resistance, but generally speaking, like if they're the same size inductors, the DC resistance usually goes up. Like if it occupies the same physical space, the DC resistance goes up with inductance. Um, so I don't know. Are they using like really awful inductors for this graph? Like I don't get it. And why would you do that in what is like basically like a marketing brief for your product? Why would you nerf it with crappy inductors? Like, aren't you trying to sell power stages to people? Why would you do that to them? Um, oh, these are active apparently. Yeah, and these are oh well, these are terrible. Oh, this is 1 volt. Oh, okay, so these aren't actually that bad. Because the thing is, as your output voltage gets lower, your efficiency gets a lot worse. Um, right, so this is 1 volt, and these are these are 2020 as well, so these are pretty old compared to these. And they look kind of similar to the because this is 1.2 volts and 600 kilohertz, and this thing is reaching what is it like? It's not reaching 92%, and this is 90. Yeah, so this is like touching 92%, but it's at much lower current. So, okay, that kind of makes sense. Oh, it says new for the 6.5 series. So I guess let's take a look for one of those. Oh, we're not going to have performance curves for that because it's too new. Yeah, this is 6 page. It's really annoying how like it doesn't say if you're going to get a full data sheet or just like a product brief. Or like if it's going to have performance curves or not. Another 2020 part. This is a 50 amp part, but also like higher peak efficiency again. And that's complete converter efficiency. So this is not just the power stage. I don't get how the peak efficiency on these is so low. It's not like they're running them at some crazy switching frequency either. Like, yeah, 600 kilohertz is kind of high, right? Because, like, you can see this is done at, like, 300, but there's a 500 kilohertz curve, and that's not that bad. I mean, the 800 kilohertz is, but, yeah, man, that 800 kilohertz curve is painful. And this is at 1.8 volts. But, like, 500 kilohertz to compared to like, and on most motherboards, you'll see 500 kilohertz switching frequency, which is another fun thing where it's just like, I'm not sure if like server boards generally prefer higher switching frequencies or something, but like desktop motherboards will generally be like 400, 500 kilohertz these days. And it used to be that they would all run at like 300 kilohertz. Actually, some boards still run like super low switching frequencies out of the box because it's like a really easy way to get some extra efficiency. Just don't turn the MOSFETs on and off a bunch for no reason. But yeah, so I am annoyed by this. And the video is now 40 minutes long. Well, that didn't go according to plan, did it? But yeah, so like I just don't know what to do about this because it just makes like my main frustration with this is it like makes the Asus in the PCB breakdowns the Asus boards look absolutely terrible because if I you know, these are the only numbers I have for these Vishay parts and those numbers are terrible. So, like what am I supposed to do? Right? And then when I've tried to like test it, they still didn't look that great. And I mean, I can't try to do a direct comparison for the Strix board because I don't have another ITX with a 10 phase on it. I do want to do a test of like the Heroes VRM with no VRM heatsinks against like, because I have the X670 ProArt, which I think that's like 18 or 16 50 amp or well. So there's a 50 amp version. There's a 50 amp part with that part number, and then there's like a special Asus version of that part number that's supposedly 80 amps. I really strongly suspect it's just the 50 amp part with an extended current limit. But anyway, and I do also have the X870 Tomahawk, which is what was it, 1480 amp parts. Yeah, so I guess I could do like a great big test of like just motherboards with no VRM heatsinks. Because that's as close as I can get to isolating the power stage performance without building test boards, which is just not practical. Which like I don't want to deal with that. That's just a pain. So I think I might still do that where I'll do the like the ProArt and the Tomahawk. I still have the X670 Elite, so that's like 1670 amp power stages. And just see like again, you know, we're not controlling for the power plane designs, we're not controlling for the inductors used, but well, Asus likes to use really high inductance inductors, which again is just like, well, it's not really like it's not really my fault. Like if those are actually increasing the operating temperatures of the power stages, maybe you shouldn't use them. ProArt is 16 power stages. Yeah. And the ProArt's like PCB should at least be kind of similar in its like layout and thermal properties to the Hero PCB. Because they're both Asus boards. So it does the, it does the thing where the SoC VRM is jammed in between all of the other phases. So yeah. Well, sorry for wasting your time, because like I mentioned this during the video, this doesn't actually matter that much. It just annoys me, because it's like a marketing thing, and it's now... And I don't like marketing, especially when it's like, oh, look, bigger number, better. And then like, but is it better? Is it really better, Asus? Is it actually? Because I've been struggling to find any evidence of such for these parts. And the thing, and honestly, actually, you know what would frustrate me even more is if like some 70 amp power stage actually made the board run cooler. That would be worse, wouldn't it? Because it's not just... Because that basically means that, like, Asus is using worse parts just so that they can advertise a bigger number. Again, when I say the board would run cooler, maybe it would run, like, 5 degrees cooler or something. So not, it's not like it radically changes, like, how good the board is. And on the ITX Strix, like, it's not going to have a problem powering a 9950X. It actually doesn't have a problem powering a 9950X. I've run the 9950X on the board a bunch. It really doesn't have an issue with it. But it could run, like, if it ran better with 70 amp parts, I'd rather have the 70 amp parts. Right? That's my main issue with this. I don't care if you can't put 100 billion amps on your marketing page. I want the most efficient VRM possible. And if that is achieved through 70 amp parts or 90 amp parts, then use the 70 or 90 amp parts. And probably the 90 amp parts, because, like, again, if this efficiency curve from Infineon is real, these things are insane. Like, actually just completely insane in terms of efficiency. It's a real shame. Like, these, I've seen these, there's like two motherboards that have used these, and a GPU. And that's it, as far as I know. The ASRock 6900X OC formula and 6950X OC formula, and the Unify X for the B550 Unify X and the X570S Unify X, if I remember correctly. So yeah. Anyway, sorry for wasting your time, because it doesn't actually matter that much, but it just, it's just like it's an annoyance I have. I care entirely too much about power delivery. And well, mainly, it's not even about the power delivery to me. It's mostly about the advertising part of it, where it's just like, oh, we have this part that is advertised as being super amazing, and it very well might not be. And that annoys me, right? A lot. So I'll actually press the stop button this time. So thank you for putting up with my rant. Hopefully you found this interesting. Yeah, I don't know. If you did find it interesting enough, I might actually put more effort into testing this sooner, like going through all of the boards and running them with no VRM heatsinks, because it's not really a priority for me right now. But it is something I definitely want to do at some point, because, like, yeah. Are these actually any good? Are they? I must know. But anyway, yeah, so thanks for watching. Like, share, subscribe. If you'd like to support the channel, there are links in the description that you could check out, and that would be much appreciated. Yeah, that's it. So thanks for watching and goodbye.